In this video, we're going to talk about complex numbers, which is one of the first topics in the S6 syllabus. So let's start with a simple question. What happens if we try to solve the quadratic equation x squared plus 1 is equal to 0? Well, what you will end up with is that x squared is equal to minus 1. And at this point, you would be left with no real solution, as you can't square root a negative number. This, plus or minus square root negative 1, is unreal. This is why mathematicians invented a new number, which is the square root of minus 1, which we call I. They said that this number, square root of minus 1, is equal to I. So this would allow us to solve this equation. We would say, well, here we can see that there's square root of minus 1. So x here is actually plus or minus I, and that gives you a solution. This allows us, as you can see, to solve equations that previously had no solutions in the real numbers. Now, something that's also very important to know is, once we know that square root of minus 1 is I, we know what I squared is what. So I squared would very simply be square root of minus 1 squared, which solves to the squared and the square root cancel out, minus 1. Let me write that a little bit neater. Then we can keep going. What is I to the power of 3? Well, I to the power of 3 would be I squared, you could say, times I. So you could say it's minus 1 times square root of minus 1, which is equal to minus square root of minus 1. And then you might ask, well, what is I to the power of 4? I to the power of 4 is I squared times I squared. So that would be equal to minus 1 times minus 1, which is equal to 1. So as you can see, this imaginary number can be used in so many different ways, and it will help you with solving equations that were previously impossible to answer. Using this new number I, we can define a complex number. So a complex number is any number which is in this form. Z is equal to A plus IB, where I is the imaginary number, B is a real coefficient, and A is a real number. So let me highlight these to make it clearer for you. I is the imaginary number, B is a real coefficient to the imaginary number, and A is a real number. So as you can see, we can think of complex numbers as an extension of the real numbers. Now here we're going to have some examples. Say we had 3 plus 2i as a complex number. Z is equal to that. We could say that 3 is the real part of the number, and the imaginary part of the number is 2. There's 2 times the imaginary part. Now, what if we were to say z is equal to minus 5i? What would we say then? Well, there's no real part to the number, so the real part is equal to 0, and the imaginary part is equal to minus 5. The real coefficient to the I is minus 5, right here. Now, if we just had z is equal to 7, this number is purely real. There's no imaginary part. So you could say that every real number is also a complex number if we think about it as something plus 0 times I. You could think of it that way, but I wouldn't. I think it would be a bit too confusing. This is just a real number. We can also picture complex numbers on what is called the complex plane. So if I were just to map this out, here we have a complex plane with the imaginary part on the horizontal y-axis and the real parts on the x-axis. So here we have imaginary, and here I'm going to put real. So here I'll just say 2, 4, 6. So for example, the imaginary number 3 plus 2i. We could plot it as, if we find 3 on the real plane, the real axis, right, 3 across, split a little dot, and then 2 up. Boom. So we could plot the complex number 3 plus 2i right here. So this means that complex numbers are not just abstract algebra, but they also have a geometric interpretation. However, in S6, you won't really be going over the complex plane. You might with your teacher. I didn't really go over it a lot. This becomes very important in S7. We're going to start handling complex numbers geometrically. And yeah, but this is something you can keep in mind, and maybe it will help you with better understanding what a complex number is. Now that we know what a complex number is, let's see how we can do some basic operations with them. So we'll start with addition and subtraction. This is the simplest operation because all we do is combine the real parts with each other and the imaginary parts within each other. So if we have two complex numbers, say z1, complex number 1, is equal to a plus ib, and say z2 is equal to c plus id. Here I left up here the little indication so that you can always refer to it if you're confused about anything. So here, if we refer to it very quickly, complex number 2, the real number is c, the real coefficient is d, and the imaginary number is I here, right? The actual imaginary number is this whole thing, so it's di, you could say. So if we have two complex numbers, these, then z1 plus z2 is equal to the addition of both real parts, so the addition of a plus c plus the addition of bi and di. So you can rewrite this even simpler as a plus c plus I times b plus d. Okay, so just like addition, subtraction works in exactly the same one. Subtraction is you just subtract the like terms. So if we did z1 minus z2, then this would be equal to a minus c plus bi minus di, which we can rewrite as a minus c plus I times b minus d. There you go. Now let's actually apply this with numbers. So let's add the complex numbers 2 plus 3i and 4 minus I. So what do we do here? z1 plus z2. What are we to do here? Well, very simply, we're going to start by saying it's 2 plus 3i plus, open brackets, 4 minus I. We can just very simply write it like this to begin, to not confuse us. And as you can see here, we just have to do 2 plus 4. Just add the real parts together and add the imaginary parts together. Plus, here we have 3i, and here we have minus I. And this would be equal to 6 plus 2i. And there you go. You have the addition, which is equal to 6 plus 2i. The addition of both of these complex numbers is equal to 6 plus 2i. Now, if we were to do another example very quickly, I would try this one yourself if I were you. Pause the video once I've written this out and try to do it yourself. So 1 plus 6i plus minus 3 plus 2i. Pause the video, try to do it yourself, and I'm going to do the working out right now as well. So again, here what would we do? Well, we would first add the real parts together. So here you can see that the real part of the first one is just 1, and the real part of the second one, we're adding minus 3. So we're going to put minus 3. And what is the imaginary part now? we have 6i. And to that we have to add 2i. So if we then actually calculate this, 1 minus 3 is minus 2, plus 6i plus 2i is 8i. There you go. It's that simple. Your answer is minus 2 plus 8i. Now we're going to move on to multiplication of complex numbers. So if we have two complex numbers, and we want to multiply them, so if we want to do z1 times z2, this would be like if we expanded it, saying, I like writing it in the form bi. You could rewrite it in the form ib. I prefer writing it in the form bi, it's more natural to me. C plus di. So it would be like writing this out, and you can recognize here we could literally just FOIL it. So we could FOIL it by saying it's a times c plus a times di plus bi times c plus pi times di, right? So you could FOIL it. So this would then be equal to ac plus adi plus bci plus bi times di. Now this is the part which is interesting. So how can we rewrite bi plus di? Well, if we expand this, bi plus, bi times di. How could we rewrite this? Well, it's very simply b d times I squared. But what did we say I squared was again? Remember, I is equal to square root of minus 1. Therefore, I squared is equal to minus 1. Therefore, we can rewrite this as minus bd. And there you go. If we were to rewrite this, we can simply rewrite it as minus bd. Now, let's put this into practice. So let's do 1 plus 2i times 3 minus I. So if we were simply to kind of go through the FOIL method, you can literally go through the FOIL method if you like. I'll just do it without drawing the arrows. 1 times 3 is 3. 1 times minus I is minus I. Plus 2i times 3 is plus 6i. And now this is the more difficult part, and this is the process which is very important to get used to when dealing with complex numbers. Plus 2i times minus I. So let's just write this out really quickly so you don't get confused. At the beginning, when working through these calculations, I would write it out like this, but you'll very quickly realize how easy it gets. So let's just rewrite it so you can get to the next step. 3 minus I plus 6i is equal to 3 plus 5i. So this would be minus 2i times I. I hope you saw what I did here. I factorized out the minus and said it's minus all of this. Just to make it easier for us, because this is the first time I'm showing you a multiplication calculation with complex numbers. So now that we're left with this, we would say minus 2i times I is 2i squared. Right? Let's leave the minus outside of these brackets. But if you remember, we had said that I squared is equal to minus 1. So let's use this into this calculation, right? Let's write this out neatly. So here I wrote it out, minus 2i squared is equal to 3 plus 5i minus 2 times minus 1. Okay, now that we've gone here, it's pretty straightforward. We're just gonna get rid of the minus 1 and turn this sign into positive. And as you can see, there's no quadratic formula in terms of I. There can never be a quadratic formula in terms of I, because I squared is simply just minus 1. So the I squared will always be factored out as minus 1, and we're just going to be left with another complex number. That's what's very important to note, is that when you multiply two complex numbers, by each other, I'm just going to write it as complex number squared, you're going to be left with a complex number. Okay, ignore my handwriting here, it's not great, but this is very important, and this is one of the essential steps when understanding complex numbers. You'll just get used to doing this once you've done a bunch of exercises, and that is very important. Okay, so now finishing off this calculation, we're going to do like terms together. So 3 plus 2 is equal to 5, and then we're left with 5i. So there you go. This is the answer to this multiplication of these two complex numbers. And I hope you can see that it's actually very easy. Once you've done all of these steps over and over and over again in several exercises, you'll just get very used to, as soon as you see this kind of initial step, you'll get very used to just cancelling out the I squared and making it minus that, right? So I'm going to show you that in the next exercise. Let's do 2 plus 3i times 2 minus 3i. Now this is going to introduce us to another topic, to the next part of this video, but let's just do this for now. Okay, let's just keep expanding. 2 times 2, this would be equal to 4, minus 2 times minus 3 is 6i. You might already notice where this is going. Then 3i times 2 is plus 6i. And 3i times minus 3i would be minus 9i squared, which would cancel out when you put plus. So this would be equal to 4 plus 9, 13, plus minus 6i plus 6i is just 0. So we're just left with 13. There you go. So here you might notice that the imaginary parts have cancelled out and we're left with a real number. Now this happens because these two numbers, right here and right here, these are conjugates. And we're going to talk more about that next. Before talking about complex conjugates, I want you to do one exercise alone and pause the video and then we'll correct it together. So how about 3 plus I times 2 plus 5i? Do that alone and we're going to correct it. Pause the video. Okay, so this is equal to 6 plus 15i plus 2i minus 5. So here you see I directly skipped the step. I directly identified we would get 5 plus 5i squared, so I just put minus 5. And this is equal to 1 plus 17i, very simply. There you go, that's the final answer you should have gotten. So as you can see, multiplication introduces a new idea. And that's that when we get I squared, we just replace it with minus 1. And when multiplying conjugates, the imaginary parts cancel and this leaves a real number. So this leads us directly into the next topic, which is complex conjugates. So every complex number has a conjugate. So if we have the number z is equal, the complex number, sorry, a plus bi, then the conjugate, which you can write like this with a line above it, or you could write it with a dash above it. Sometimes you have both notations, completely different, depends on your textbook and your teacher. This would be equal to a minus bi. So the conjugate is the same number, but with the opposite sign in front of the imaginary part. Here we have positive, and then here we have negative. So moving on to examples and exercises, if I were to tell you that that the complex number z is equal to 3 plus 4i, what is the complex conjugate? So once you've answered it in your head, hopefully, the complex conjugate is equal to 3 minus 4i. Okay, if z were minus 2 minus 5i, then what is the complex conjugate? The complex conjugate would be minus 2 plus 5i. Now, if you have the complex number z is equal to minus 7i, the complex conjugate would very simply be plus 7i, right? Because there's no real part to the complex number. But the imaginary part still has to have an inverted sign. Okay, you might ask, this is pretty easy, but why is this useful? Why is the conjugate useful? Now, you might remember how we used it in multiplication and we ended up with a real number, right? So let me show you what happens when we multiply a number by its conjugate. Let's do z times its conjugate. This would be equal to a plus bi times a minus bi. Now, if you expand these brackets, this is equal to a squared minus abi plus abi. Look out for the I squared here. Minus b squared times I squared, which would just cancel out, and we would get plus b squared, right? So now we have a squared minus abi plus b squared. These cancel out, and we're left with a squared plus b squared. So now we're just left with the sum of the two squares, which is really easy to calculate. For example, take z is equal to 5 minus 2i. Its conjugate is equal to 5 plus 2i. If you were to multiply them, please multiply them. And I'm going to work them out right now. If you were to multiply them, you would get 25 minus 10i plus 10i plus 4. And this would leave you with 29, 25 plus 4, because these cancel out. There you go. So the result is purely real. Okay, let's do some more exercises together. Say you have the complex number 9 plus 4i. Multiply it by its conjugate. Normally here I don't even have to write its conjugate. You should be able to see exactly what it is. So this would be equal to 81 plus 16. I skipped all of the steps, and you can use this equation if you want. You can very easily just go through the steps and figure it out though. And you're left with 97. This gets, again, very easy once you've practiced it a couple times. Okay, so now that's enough practice, and this is what leads us to dividing complex numbers. Okay, so now that we understand the conjugates, let's use them for division. Dividing complex numbers isn't just as straightforward as dividing real numbers, because we can't leave an imaginary number with a denominator. So the trick is we multiply the top and the bottom by the conjugate of the denominator. That way the denominator becomes real. So if we have a fraction a plus bi over c plus di, we would multiply the top and the bottom by the complex conjugate of the denominator. So we would multiply it by the complex conjugate of c plus di, which is c minus di. Now the denominator will become c squared plus d squared, which is real, and therefore we would get the answer. So let's divide 3 plus 4i by 1 minus 2i. Okay, so to divide this, we would multiply both of these by 1 plus 2i. Okay, and this would give us, at the denominator, 1 squared plus 2 squared, 4. And at the numerator, we have to expand. So this would be 3 plus 3 times 2i is 6i, plus 4i times 1 is 4i, plus 4i times 2i is equal to 4 times 2, 8, 8i squared, which we know would be minus 8, right? Is equal to 3 plus 6 times 6 plus 10, 6 plus 4 is 10, sorry, 10i minus 8, the I squared is equal to minus 1 over 5. And then you get the answer, 3 minus 8, you get minus 5 plus 10i over 5. And here you can very simply write it as minus 1 plus 2i. There you go, final answer, minus 1 plus 2i. Now let's try another. 2 minus I over 3 plus 4i. please do these yourselves and then look at the answer. We're going to first multiply by the conjugate, 3 minus 4i, 3 minus 4i, and this would be equal to, if we expand the top first, 6 minus 8i minus 3i, or let's minus 4, right? Because you would have plus 4i squared, so that'd be minus 4. All of that over 3 squared is 9, plus 4 squared is 16. This would be equal to 6 minus 4, which is 2, minus 8i minus 3i is minus 11i over 25. Okay, now this is important, right? You would get this, you probably have this as your final answer right now, but if it is asked to leave your answer as a complex number, to write your answer as a complex number in the complex number format, you have to rewrite this as is equal to 2 over 25 minus 11 over 25i. You have to have the separation of what is the coefficient and what is the real number, and separate that from I. Okay, this is a correct answer, probably your teacher might give you the mark for it, but if it asks for this specific format, this is how you would rewrite it. Okay, so now we know how to add, subtract, multiply, and divide complex numbers, and now we're going to look at how they appear as solutions to quadratic equations with negative discriminants.